Okay, great. So I guess I'll get started then. Can people see my screen? Yes. Is this okay? Good. Nope, that's not what I wanted. Okay, yeah, here we go. Hope, yeah, let me know if at any point my slides aren't making any sense or if you can't see them. But yeah, I'll get started with online algorithms. So let's just talk about what an online algorithm is. We know what traditional algorithms are. They take in a whole bunch of data, an input, they solve a given problem, and then they give you a solution. So a great example is these sort of assignment problems. Maybe I have a whole bunch of servers and a whole bunch of jobs. Some jobs can be completed in some servers. They can't be completed in all of them. For example, this first task can be completed at the first and third server, but not the second server. And you have all these, these jobs and these servers, and you want to find a way to complete every job. So just with this example that I've drawn here, we can see that there is a way to complete every single job. So that's great. That's usually what most algorithms over time have done. But now we might be interested in a different setting, online algorithms, which take in a stream of data and have to make irrevocable decisions on the fly. So the online version of the problem that I stated before is I have a whole bunch of servers and jobs are coming online. It's a stream of jobs. And at every point in time, whenever I receive a job, I need to match it to a server and complete that job. So for example, I have all my servers on the right and I have a job that comes on the left and I see that it can be matched to server 1 and server 3. And then I'll have to make some decision. Maybe I assign it to server 3. And then the same thing happens with another task that comes in. One thing I should note here is a server can only take in one job or can only complete one job. So I can't assign 2 jobs to the same server. So I'm trying to find basically a matching in this graph. In the offline setting, I'm looking for a perfect matching, and in the online setting, I'd like to maintain a perfect matching as jobs come in online. So do people have questions about the setting or the problem?
I assume the jobs take varying amounts of time.
Yes, so that's a good question. So maybe like a much more like intricate and maybe useful problem than what I'm saying is the scheduling problem. Maybe jobs will take certain amounts of time and a server will be occupied for that amount of time, but once the job is completed, it's free again. That's also a very nice online problem. I'm just gonna make it real simple for the setting that I'm saying, which is that it's just a very big job and the server is occupied for a long duration. And yeah, it's just one job goes to one server and you're just trying to do a matching. I'm just talking about this setting. It's because it's the one that I've been working on, and it's a hugely rich field. But like you say, scheduling is definitely really a big thing as well. Okay. Yeah. More questions.
Are some servers better at performing certain jobs than others, or are we just assuming that they're all on the same degree of proficiency regardless of it?
For just my setting, I'm going to assume it's 1 or 0. Either the server can service that job or it can't. So that's what the edges are going to be representing. Like for the first task that's coming in, it can only be completed in server 1 and server 3. But maybe you might consider some sort of weighted instance and you're trying to maximize like your best perfect matching. That's also a really good problem that's very, very related to this. Yeah, but I'm just going to assume this very simple instance. All of those are valid.
I see. Thank you.
Yeah. Okay. I'm glad that people like this problem. I wasn't sure if it would be popular, but I think it's really fun. So hopefully it'll be of interest to you guys. So the goal of an online algorithm is, well, it's to do well, but clearly we can't do as well in an online setting as we may expect to do in an offline setting. And in a few slides, we'll work through an example and see exactly where being online will end up being harder. And So the last example I was talking about was maximum matching. So offline, it's pretty easy to find a perfect matching between, jobs and servers, but doing this online, it's at least not like trivial to do as well. So then how do we quantify what it means for an online algorithm to be, doing well? This term is, or this quantity is often called the competitive ratio of an algorithm, which is just over all instances, what is the best that your algorithm can do? And so in particular, I'm, over any instance, I can guarantee my algorithm does, at least half as well. And then the competitive ratio would be half. We're aiming for 1, right? It'd be awesome if for every single instance you do as well as the offline setting, right? But that's not exactly like that's something you don't really expect. So maybe you expect it to do half as well. Or maybe in the really hard problems, the problems where you need to be doing a lot of things offline, you might expect it to do 1 over a log or something like that. But 1 would be great, or something close to 1 would be nice. This is the goal. And let me just take a step back here and talk about why we care about the online setting. As we all know, there's like a huge amount of data that technological advancements have brought forward. Offline algorithms, algorithms that take in all the data at once, do a computation and return an answer. I mean, they need to parse all the data, and that can be expensive when you have a huge amount of information. Online algorithms, which make decisions on the fly, they don't store all the data. They store a very little amount of data. They don't need to see the entire past or the future to make decisions. And in that way, online algorithms will be able to operate under uncertainty and still be able to give you something that's like, maybe only like half as bad as the best answer or something like that. So in this case, we're willing to trade off like a perfect answer for this sort of robustness and flexibility that an online setting will give you. And so in particular, the online bipartite matching problem, or the problem that I was talking about earlier, is really, really useful in assigning ads to people that are willing to advertise. The digital ad marketplace was like, it was huge in money. It was 109 billion in just the US last year. In particular, Google, Microsoft, all sorts of websites have like a huge amount of research on this. And so that's where a lot of this research is often funded by. So the problem would be that websites have advertising slots and customers have spots, want to buy spots in order to advertise. Maybe a customer has certain slot preferences, or they can only afford certain slots. And as customers arrive and request ad slots, you want to be able to fulfill that request as soon as possible, because time wasted in advertising is suboptimal. So we see that this problem is clearly a matching problem. We want to match customers to ad slots that they can buy. But it's also something that lends itself like really usefully to an online setting. We have a lot of people, a lot of customers that are coming in, and a lot of requests that are coming in, and we want to maintain a maximum matching. Yeah, any questions about the setting, about the application so far? Please feel free to interrupt me. I might be going a little fast. Okay, so maybe let's just work through an example to make sure we know just this online bipartite matching problem. So I have these 3 servers on the right, and I know we're talking about ads, but I was a little bit too lazy to change all the pictures from servers to ad slots. So let's just give me the benefit of laziness here and use this picture as is. I have 3 servers, and I have a task that comes in. And I need to, at this moment, when this job has come in, match this job somewhere. Okay, maybe I'll match it down to the 3rd server. The next one comes in. I have the 1st and 2nd one to choose. I need to make a decision right now. So I choose that one. But then the third server comes in and the third job comes in and all the servers are occupied. And so it's clear that we can't always hope to get a maximum matching. Here, the maximum matching is 3, but we were able to get only a matching of size 2. So in this case, we did 2/3 as well as optimal. So yeah, clearly we can't get 1. It turns out that if you want to do a deterministic algorithm, the best ratio you could hope for is half. There are instances where for any deterministic algorithm you give me, I will be able to create an instance where it'll only do half as well. And a greedy algorithm is going to achieve this. So pretty simple deterministic algorithm will get you half, but half is a little bit of an unsatisfying answer. Super cool result by Karp, Vazirani, and Vazirani, the Vazirani brothers, if you know them. They showed that with a randomized algorithm, you can beat half. You can break half and get to 1 - 1 over E, which I mean, I know this stuff has a lot of cool practical applications, but it's just really cool that this quantity pops up and that you can even break half with randomness. So from a theoretical standpoint, it's just really cool. And so I really showed maybe one setting of online bipartite matching, but there are all sorts of assumptions that you can make to come up with not only interesting, but just like unsolved problems. This is a really rich area and work is being done on this like right now. What if a customer can get more than 1 ad slot? What if we know something about the distribution of customers arriving? Do we necessarily need to be doing things in a worst case analysis? In particular, the beyond worst case analysis is a huge buzzword in theoretical computer science right now. It's everywhere, and it's sort of given us a new framework to like take old problems and show, look, the worst case analysis is like this, but if you look at an average case analysis or a random instance analysis, it actually performs great. And we can imagine that a worst case analysis is not necessarily the most reflective of what real life is like. So I talked about the digital marketing or digital advertising framework for online bipartite matching, but as you can imagine, an assignment problem is going to have applications in a lot of other places. You might be interested in assigning residents to hospitals, jobs to machines, or even kidney donors to recipients. Yeah, so there's already a huge body of work in online bipartite matching, but it just grows even bigger when you just consider the assignment problem in general. Do people have any questions at this point? Awesome. And I'll probably conclude with just like mentioning offhand with where else online algorithms tend to be used. A big one is probably online machine learning. You might have a lot of data that you can train a model with, but it would be computationally very nice if you could learn a model with only a single pass over a training set. Relational databases often have a use for basic statistics about a stream of numbers. A pretty simple online problem is just find the running average of a stream of numbers. And something that is a little more complicated is find the most frequent element appearing. I mean, these are like really simple problems to state, and then they're just, the techniques are really cool and intricate and useful. So, but yeah, I could probably go on forever about online algorithms, but I'll stop here. Hopefully that was good for you guys. Feel free to ask questions. Okay, sounds good. I can pass it over to the next speaker.
Sure. Okay. Thanks, Sherry. Okay, that made a lot of sense. So actually, I'm going to speak about something that is not at all what I work in. So I'll probably struggle a bit, so bear with me. And I'm going to sort of pick it up from where Sherry left about like sort of, okay, so let me just share my screen and I'm going to just use whiteboard to say stuff. Okay, here we go. So you guys can see the whiteboard, right? Oh, great. So one important thing that sort of very important, interesting thing that Sherry said that, so one kind of very interesting way of research right now is like pick up theoretical models and then do better than worst case analysis. So now a very important question here is that like, why do like we should look at theoretical models and what kind of theoretical models can we look at and how simple a theoretical model can actually describe reality? So one thing, like one question that I had when I was looking into theoretical computer science, and even though I was really interested in the abstract and mathematical part of it, it always seemed to me that really connecting it to reality would be complicated because reality is probably really complex and really uncertain, and thus creating a theoretical model that captures all of reality is probably really hard. And then I came across this result at the very beginning of when I started exploring theoretical computer science. And this is like really counterintuitive in the sense, because this result basically showed, and it's very classical result, and we all use it even like without like recognizing that we are using it essentially. I'll tell you about that in a minute. So what this result or this theory sort of showed that because the reality is complicated and more importantly uncertain, we can actually come up with simple models. So here, what I'm going to sort of describe is that uncertainty is good. Okay, so I'm going to talk about a famed result by Shannon, and it's called basically the theory of communication. So this is essentially the framework on which all modern communication is developed. And it's a very simple model that we'll talk about. And it was created by Shannon, I think, in the 1950s. And it completely changed the way information and communication was looked at. And basically, it started this whole era of information theory, which is why Shannon is also called the father of information theory, and or rather, I think, founder of information theory. And more importantly, I think, on which is of more interest here, that the model he created was really simple. Okay, so the problem of interest is that we have a transmitter and we have a receiver. And we are going to send, let's say, digital signals or analog signals from the transmitter to receiver. And then there is nature. And these signals will get distorted by nature. And somehow the question is, how do we reconstruct this signal? And this was one of the sort of main problems that the communication engineers of the 1950s were dealing with. And they looked at it in a deterministic, you can think of it as a worst case reconstruction of signals. So this was the problem that was being handled by the engineers. And because of this deterministic reconstruction of signals, signals could be different based on the kind of data they were transmitting, and there could be different kind of noises present in the nature, and thus the problem was really complex. So against this background, Shannon came up with a very simple model as follows. So you have an information source, and then you have a receiver, and then there is an encoder, and there is a decoder. So the data is somehow encoded in using this information source, and then the data is sent to the decoder, and then it is decoded is at the receiver. And more importantly, this is the channel, and there is noise in the channel, which in some sense is random. Right. So the important part here was that before how the area was being treated at was that you had some deterministic signals and you had to reconstruct that exact signal. what Shannon had the insight of looking into is that if we can create a model where the noise can be treated as a source of randomness, then we will not have to think about how to exactly reconstruct each message. We can instead look at the whole problem as a probabilistic model, and which is what Shannon did. And it generated a lot of insights which have like changed our understanding of communication since. And as I will conclude with by saying in a few minutes later, that it's still having impact on our real world. So the first thing that Shannon created in this context was the concept of bit. I think he said that bit was previously used by someone, but I think this is the first paper in which the term bit was used, which was basically a phrase for binary bit. Yeah. So then the point of bit was, so you are trying to encode data into binary signal, so 0, 1, and that means the effect of noise can be quantified as just either flipping a bit or not flipping a bit. So just this simple theoretical modeling made the problem of understanding the effect of noise much easier. So that was the first thing. And the second thing was that noise was not going to be worst case. Rather, he defined something called, and all these things I think I have even seen like present in some school textbooks. For example, he defined something called the channel capacity. And he defined entropy. So I'll first just briefly describe what entropy is. So entropy of a source is the amount of data being sent per second, just that, nothing else. And you define it as some number of bits. And then the channel capacity is dependent on many conditions such as bandwidth and so on that you must have seen. And then you also have basically, let's say, for example, bandwidth, which is like how much, what is your source of communication essentially. And then you also have noise. So this bandwidth and noise define this channel capacity. And he basically showed, again, which is very natural to say, that this entropy H and this channel capacity C is that you can only transfer data reliably if H less than C. Transfer information reliably if H less than C. And that is in a nutshell what Shannon's theory of communication is. And then he came up with some very natural models of noise and functions for defining entropies using simple logarithmic functions. And then he described why should you use logarithms in many cases to describe noise and so on. So I won't go into very deep details of that. But like my point is that it took me like probably 10 minutes to describe this model. And it's a really simple model to understand which you do not really need any prior background. But this has basically been the cornerstone of communication. And this model, so the reason we have this model, this encoding and decoding, this also started the concept of encoding schemes, which are again fundamental to communication. And this encoding schemes also improved like previous approaches, where the previous approach would be send the same signal over and over again and hope that at some point you were able to reconstruct it. But with this encoding schemes, and if any of you are interested, you will see that there are multitude of encoding schemes, and they're really beautiful a lot of the times. And then you have quantum encoding schemes and whatnot. So these things were sort of, you could say, that were propelled by just this simple model. So my point is that in theoretical computer science, often like very powerful results that have really long-standing impact on reality come from an understanding that in fact simplicity can be the key, as opposed to like what essentially my understanding was, that to encode reality you would either have to lose out on something or you would have to be very complex. And it's true, while we probably lose out on something because you can still have some errors, in the end it is something that's realistic and works, to the point that, for example, even in the 5G spectrum, I think there are 2 or 3 encoders that are used that are proven to be efficient under Shannon's model of communication. And then, like I said, so this is sort of how he created a theoretical computer science model and how it related to reality. On the other hand, like I said, he coined the term entropy of noise channels and entropy of probabilistic models even. And this entropy has had deep lying impact in various different fields of mathematics, such as understanding behavior of dynamic systems and so on. So this, in a nutshell, is a very simple setup that has been like really crucial to our development as like development in the era of communication, essentially. Yeah. So if you guys have any questions about this part, if it made sense and so on. Cool. Okay. So this was sort of a very classical result that has really interesting impact on everything. I'll just speak of something in short. I think I'll have to stop because then the next speaker will speak. So I'll just give a very short description of something called Voronoi diagrams. Okay, so is anyone here aware of the term Voronoi diagrams? Okay, cool. So Voronoi diagrams is a very simple concept. It's a geometrical concept. Is that, let's say you are given a few points, something like this. Then what you do is between any two pair of points, let's say this point, let the points be 1, 2, 3, 4. For any two pair of points, you just draw a perpendicular bisector of the line joining them. So you basically just draw a line which is equidistant from both of them, like this. And then you draw a line like this. And then you draw a line like this. And again, something like this. Okay. And then, and also like this. So you keep on joining this line. Maybe I'll draw with 3 points so that it's easier to draw. And then you create a picture essentially, which looks something like this. And let's say there is like an enclosing box. And that's all Voronoi diagrams. Now you can also have Voronoi diagrams on higher dimensions, but let's just look into the two-dimensional case. So this is a very simple construct, and these are called Voronoi diagrams. And if you take these points and join the 2 points who share a line between them, like this, then you get something called the Delannoy triangulation. So the Delannoy triangulation is probably not clear from this picture, because the point is that no matter how many points you have, when you create a Delannoy triangulation of it, it looks something like many triangles. So this is a typical Delannoy triangulation. So now Voronoi diagrams was, I think, first used in, so this is again a discrete abstract structure. And the reason it is connected to theoretical computer science is that Voronoi diagrams and Delannoy triangulations, you can have algorithms for calculating the Delannoy triangulation of a bunch of points. And then it becomes a part of theoretical computer science in that sense. It is essentially a part of computational geometry. And it has various usage. It has usage in image compression, facial recognition, and so on. So the reason why it has usability in image compression is sort of like easy to understand in the sense, let's say we have a sort of homogeneous image where the changes in the color of the image are gradual. So you just pick out you define as points the most intensely colored points in the diagram, and then you try to create a Delannoy triangulation of the whole thing, and then just define sort of, okay, so let's say I have a picture where probably the color here is very red and the color here is very black, and it mixes in between. So you could just probably represent it as 2 points, and you just define a function as to how much the color will dissipate as you go away from these 2 points. And once you reach a middle point, then it stops, something like this. And then when you look at it in a sort of multitude of points and multitude of colors, often it has been observed that using Voronoi diagrams is really useful for image compression. And it is also used for, like I said, facial recognition. It is used when you have a picture, when you have like pictures taken from multiple vantage points, and then you want to merge them into one 3-dimensional. So if you have a bunch of 2-dimensional pictures which you want to merge into a 3-dimensional overall object, then again, this Delanoy triangulation really helps because it has really nice geometric properties. So it's some way, this is a very discrete structure that has impact onto our current understanding of machine learning and image processing, whereas like this was created like far back. So the first time Voronoi diagrams were used, this is like a small story that I'll conclude my talk with, piece with. So it's a small story that I think Voronoi diagrams were used in the, I don't remember the exact year, 1800s cholera outbreak of London. So this was actually used by a professor called, a doctor called, I think his name was Dr. Snow. So he used this in a 19th century cholera outbreak to figure out like what was the source of the outbreak. And in some sense, it was also the first time a disease was studied in such a analytical manner. So what they did was, so in London, there were many water pumps, let's say P1, P2, P3, and so on. There are many water pumps. And then what Dr. Snow did was he created a Voronoi diagram of this whole point set, and then realized the area that was covering. So in Voronoi diagram, you would have like many areas like this, and so on. So what he observed that the points or the areas which was inside this area, inside this face of the Voronoi diagram, had much more cholera outbreak than the other case. So basically the point was that whenever the closest pump, let's say water pump to people was this particular water pump, they were getting cholera. And once you have this way of looking at it, it was really easy to sort of observe the source of the disease and then work against it. So this was something, my point is, again, this is something that was created like almost 200 years back now for a completely different purpose. And then we see it being used quite, like, I don't know if it's still being used or if there are like more advanced ways of working with image processing and so on. It's not really my area, but I know for a fact that it was used even until early 2000s and early 2010s in many areas. Yeah. So that's sort of, again, small explanation or small exposure to how theoretical computer science can be connected to reality and how it is inspired by reality as well. Yeah. Thanks. Okay. So if you have any questions, otherwise I think Kostas will speak next.
Yeah, I see no questions. So yeah, thank you. It was very nice, both of the topics. So yeah, let me share my screen. Do I have any? Let me see. Okay, can you see my screen? Yeah, great. Okay, so I know it's been a long day probably for all of you, so I will try to make it quick as possible. So yeah, I'm going to talk about AdaBoost, which is an algorithm. It is a learning algorithm, or rather a learning algorithmic paradigm, because it works for many different problems. Which was initially motivated by theory, but eventually had a very practical and useful application. And I think it became a trend at some point also. Yeah, so what was the problem that I will first talk about the application, although the algorithm was discovered before the application. Okay, so the problem that I'm referring to is face detection, where we are given an image or rather we're given many images in real time, and we want to to point to the places of each image that we receive in real time, and to point quickly to the places where there are faces, human faces. So yeah, so the problem here is that typically in learning, one problem is there are various learning problems, but one problem is classification. So you want to output something, a value that is either 0 or 1. So this problem is not of that kind. We don't want to output just whether there is a face or there is not, but we want to find the place, all the places where faces are. And this problem was solved by a very efficient algorithm by Viola and Jones in 2001. And here are the results. You have probably seen, or maybe some of you which are more senior have even implemented that in standard computer vision courses. Yeah, so you really give an image, and then you receive this bracket, these boxes around the faces. And yeah, okay, there are some mistakes at some points, but yeah, but by the way, do you see my pointer or not? Can you see the pointer? Yes. Yeah. Okay. Yeah, so there are some mistakes made, but the reason that this is very useful or interesting is that from the moment you give an image, less than only a fraction of a second passes until you have every face circled. Okay, so what is the idea behind that? So when I'm given an image, what I could do, so in some sense we know how to classify a given image, whether it is a face or it is not a face, or we can hope that we can do that, make that work. But what we don't know is how to find all the faces in a given image. So given an image, we consider all possible squares and we search for faces there. And if we classify a small image, a sub-image, as being an image containing a face, then we just put a bounding box around this sub-image. The complication is that because we have to brute force over all the possible boxes, there are too many evaluations needed, even for a single image. So what really we'd like to be true for our algorithm would be when our algorithm is given a small image, a sub-image, it will very quickly decide whether it is a human face or it is not. We really want the inmost loop to take only a really small amount of time. Okay, and in order to do that, Viola and Jones use the HAR features, which are very simplistic ways to extract information out of an image. They're very crude, and they are based on observations, very simple observations, like, for example, that the level of the eyes, the shades of a human face make this area darker than the area below it. So what HAR features do is, so one HAR feature is one real value, and it corresponds to putting this one kind of mask. This is a mask. This is one kind of mask, and we put it on a specific place on the image. we again have to brute force over all the possible spaces because we don't know where the eyes are. So we really have to put the mask in all possible spaces, and then we would for any selection of the place that we put the mask, we would have one real value that would be computed as follows. The bits, so every image is a bunch of bits. So the bits that correspond to the white area would be added. We would sum over them, and then we would subtract the bits of the dark area. And that what would that mean? That would mean that if the value that we get is large, then this is consistent with the belief that this part of the image could be the area of the eyes and the nose, because the area of the eyes and the nose has this property that there is more dark to the level of the eyes. Okay, so this is very crude, and you would not, I mean, if you had just one value that said, okay, this is consistent with that belief, that this is eyes and the area below the eyes, then that would not be a good classifier. You would not say, okay, this value is very large, so that is a face, because in the first place, this mask is not a face, right? So this really does not make us very confident about believing that this is a face, but it says something about whether this image is a face. So yeah, the problem with this hard features is that so there are various types. So this is one type, which is this simple observation, but there are other types, which, for example, this the second type uses the structure of the nose and etc. There are like 4 types that were mainly used, and the problem is that because we have to put these masks over all possible places in even a small image, then this would give a very large number of real values which are different. So we would like to find a way so that we use all this, we combine all these small amounts of information given by these features, this pool of features, but we would also want that we can find a small number of important features, and we really do not evaluate on test time all the features, because the features are too many to have this very quick response that we are hoping for. So we would like a classifier that would do the following, would say, okay, I take a training set, which means I'm not in the evaluation setting. I'm taking a lot of images, and I'm trying to find a way to do something a priori, and then apply it to test data, because I want to be fast in the testing phase. And in the training phase, I want to discover the important features. I want to discover which are the places where really I could find a face. Yeah, so and the ADA boost algorithm does exactly that. It finds the important features, and also a very simple way to combine them. Okay, and this simple way is based on a very a fundamental important property, which is that we have some very crude way to some very small, some very easy way to say whether a given image has some small probability over to be some larger probability than just 1/2 to be a face rather than not be a face. So we really need just a small advantage. If we have an algorithm that can achieve a very small advantage over saying randomly, yeah, this is a phase or this is not a phase. So if we have an algorithm that has a very small advantage, then this AdaBoost algorithm can boost this algorithm in a clever way in order to come up with a strong algorithm, in the sense that this algorithm will say with confidence whether this image is a phase or it is not a phase. And the feature and in the meantime, what this algorithm comes up with, this function that takes an image and outputs whether it is a phase or not, it is of a very specific form, which is very important in our case for phase detection, because it really finds the important features. So what one could do, we could just instead of considering all the possible important possible features, we could just focus on very small number of features and decide whether this has some probability of being a phase, and then we discard other areas, and then we do that in a cascading way. We use more and more features. But anyway, these are mostly details. The important thing is that the AdaBoost algorithm was not designed for this problem. The AdaBoost algorithm was, people had come up with it like, I think, approximately 5 or something years earlier. The reason that they thought about this algorithm is that it had a theoretical motivation. So learning theory is a very, as for example, we heard in today's lecture, learning theory is a very vast field, which was many of the things, the results were known by statisticians even hundreds of years ago. One particular problem is that although we know how to exploit in a best way the samples that we get for a classification problem, we don't. This algorithm that exploits the samples in an optimal way is not necessarily efficient. It might be very slow. So people try to think of ideas of how to, to find other algorithms that would be more efficient in this task. So yeah, so AdaBoost was used this idea that you would run some very simple algorithms that have only a small advantage over classifying randomly the phase or anything, and then they would boost it with a very efficient procedure. So if there is an efficient weak learner, then there is an efficient strong learner, and everything, and this reduction is essentially efficient computationally. So, but that all of this was referred to the training phase. The application of that Viola and Jones came with was another property of this AdaBoost algorithm, and this property was that the actual classifier that AdaBoost creates has a very interesting structure. So with that, I would say that if one wants to delve deeper into the learning theory, I would really suggest reading this book, Understanding Machine Learning from Theory to Algorithms, which is it has various levels of difficulty. So maybe you could start with something like the first chapters, and there are also books specified on boosting, which is notion. Yeah, so that's all I had to say. As a final note, I would say that yeah, so machine learning it has very great applications, and many of them do not use exactly theoretical results, but it's better and more. There are many motivations for trying to create algorithms that have provable guarantees in the machine learning setting. And this algorithm AdaBoost really had a very strong impact. And yeah, and interestingly, it was based on a result that had a different motivation, but people like understood this problem very well, and they applied it to a very specific setting of face detection. Yeah, that's all from me. I hope it was interesting and not that tiring. Yeah, thank you.
Yeah, thank you. Yeah, that was really good. I think this is basically it. We'll conclude this talk for today, but please feel free to direct message us if you found any topic particularly interesting. The goal of the summer school is to help you find something that you guys think are cool at the end of this. So yeah, I think that'll be all. Thank you.
Cool. Thanks, Sherry.
Thank you.
Thank you.